Okay, question 8. We've got a question about the Rutherford experiment with alpha particles fired at gold foil. So the first one is, it was found that alpha particles were scattered by gold foil. It tells us the thickness of the foil, so we know how thick it is. It tells us the diameter of one gold atom is 0.15 nanometers. So that's 10 to the minus 9. So we have to do that change. And then estimate how many gold. So, well, we know it's going to be this divided by that will tell us how many there are. So the number of atoms is the thickness divided by the width of a single atom, so we can get the next one and the next one and the next one. You've got to remember to change nanometers. This is in meters, so that's perfect. So 0.15 times 10 to the minus 9. Put that into a calculator and you get 2,666. I think the mark scheme said it would accept approximately 2,700 atoms. But we're going to put the right answer in, the full answer, because it doesn't ask us to give a specific number of significant figures. Okay, on to the next part then. The apparatus was used, and we can see we've got these different angles. So most particles were detected in this area, and then we've got a graph where it's showing us the number of particles for each of these angles, and they've plotted a graph. So it says, use information from the graph to estimate the ratio of the number of particles scattered through 5 degrees to the number of particles scattered through 100. So if that's going to be 10 degrees, 5 degrees is here, and we can see that's 10 to the power of 6.5. 100 degrees, I'm going to read across there, we can see that's 10 to the 2, and we're just going to write those as a ratio, 10 to the power of 6.5. to 10 to the power of 2. Do a bit of maths and it'll tell us our unitary ratio. So 5 degrees to 100 degrees, 10 to 6.5, 10 to the power of 6.5 from the graph. The other one is 10 to the power of 2. Divide 10 to the 2 into 10 to the 6.5. Now you know from maths, you just subtract the indices. So we're left with 10.445 to 1 would give you a mark. If you then actually shove 10 to the power of 4.5 and you calculate, you get that. That is also a mark. That accepts either of those. Next one, really common question, so be good at this. Explain how the difference in the number of particles scattered gives evidence. So most pass through. This shows that atoms are mostly empty space. Now, we always do most, some, a few. Some are deflected, less than 90 degrees, showing the nucleus is positive because it's been repelled. And there's your model answer, been repelled by the same charged alpha particles. And then a few were scattered more than 90 degrees. You are happy to use in there reflected, showing the mass of the atom is concentrated in a small central nucleus. So to go through, most pass through, mostly empty space. Some deflected, this is because they've been repelled. And then a few were scattered or reflected. And this is a small central nucleus. So that's the key parts. Common question, and it's what's nice about that. You practice it a few times, gets you marks every time. Next part, we've got a apparatus and a protractor, and it says describe how the students could use the apparatus to model the scattering. So you can see we've got a marble. We're going to roll it down, and then clearly once it's done its thing, we're going to measure the angle from this normal. So we're going to need a protractor. It tells us we've got one, and some will do that. Pting, some will go over there. We'll get the basic idea of what's going on. So roll the marble down the slope for a mark. So it's just look at what's going on, measure where the marble ends, and measure whatever that angle is with a protractor. There we go. So give one limitation of this model. Well, the crucial part is everything about this previous one. We had this idea of charge. And that marble only has mass. So the limitation of this model is it only has mass and no charge. Or I could even argue it's a 2D plane rather than a 3D model. But I think the idea of mass and charge is well worth making sure you understand that. Okay.